Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're gonna talk about gravitational waves. So let's dive right into it. Well, first we have to understand this part very critically. Gravity. What the heck is gravity? Gravity, in simplest term, is a fundamental force. Now you have to understand this. For most fundamental things in this universe, we have a carrier, so to say. So electricity, electron, energy, photons, gravity, no clue. So we call it graviton. Basically, it's an x variable. Find x. So we just call it graviton. But it's a fundamental. Like it's as known as it can get. Like it's solid. It's absolute. Like you can have a star and it can run out of fusion, but gravity, it does not care. It will run till infinity. So like gravity does not have an expiry date, so to say. So gravity is fundamental force. Now what the heck does it affect? Like electricity, when I say, generally it affects conductors. It's not going to do much to basically insulator. So conductor is it's kind of carrier, and if you can remove electron itself, well, electricity has no meaning. So what happens in case of gravity? What does gravity affect? Gravity affects what we call space-time. Now space-time, you have to understand this, space and time are bound together, and we live in four-dimensional world. So we have length, width and height, basically x, y, z, and fourth dimension is of time. Now that time is bound with all these three dimensions. So that's the tricky part. That's the part that Einstein figured it out, that space and time, they are bound together. They are like, part of basically side of a coin, so to say. Now when you bend space and time, if you assume it as a, let's say, two-dimensional plate, when you bend it, you get gravity. Now bending it is very, very hard. For example, Earth's bends it okay-ish. It's it's respectable. We can have a moon orbiting us, but sun is like on a whole different level. It makes us orbit it because it bends it even more. Neutron star, even more. It bends so much that you can see more than 50% of it. Why? Because it will bend the light around it. Black hole goes on a different way, just ends up collapsing it. So you have to understand this, space-time is everywhere. We are inside space-time, and gravitational well is what we call gravity, so to say. Now space-time is very, very hard. So easiest example of that, moon. Big heavy object. It's not lightweight. Like we can mine moon for centuries and it would not even make a dent. But again, does it bend space-time? Very little. Technically yes, but very little. Like we can barely detect its gravitational lensing. So same happens with everything. It's a very hard. The space-time fabric is ludicrously hard. Now what about the speed of propagation, like how things propagate in it? Like electricity has a speed, sound has a speed, light has a speed. What about this space-time? Well, let's say you blew up sun, you took sun and you're like poof, poofed it, Thanos it out of existence. How long before you know it? Here's the light, we know for a fact that we'll know after 8 minutes. Let's just say that sun disappeared. Here same thing will happen with gravity also. It will take Earth to realize like around 8 minutes that there is no more gravitational that divot will take time. So it's bound by the speed of light. It cannot travel faster than that. So this is the surface level fundamentals of gravity. Now once we understand that, we understand it moves. It's not a constant thing. It has a bend, flex and all that. What does that lead to? That leads to ripples. Basically you have a water surface, you move, like even if you move gently your hand, it will cause a ripple, and if you like throw a big rock, it will have a splash. So everything causes a ripple. This is very critical aspect. When I say everything, I mean everything. Even an electron causes a ripple in space-time. Only difference is it would be like 0 dot Google 1. Now what does that Google mean here? Google means 100 0. So you get the point. Like for we troll supercomputers by that. So reality is everything causes space-time, bend in space-time, but because of the stiffness of basically space-time, it's unmeasurable, flat out, you cannot measure it. So only big massive objects causes a big ripple, and not to mention big massive object causes generally gentle ripple. So you will not feel it. It won't be like boo 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 boo. It's like something happened. Like it's very gentle. But big cosmic event, let's say two neutron stars going bit too intimate with each other, or a neutron star trying to become a black hole, or something of this magnitude, supernova, hypernova, these things causes a big spike, these things causes boom. Everything else is like way gentle, very gentle, you will not notice it. But these events, they cause a spike, like in a moment's notice, poof. So these are very, very powerful event. Now one interesting aspect of it, you have to understand, this allows energy dissipation. What the heck that means? Think of it this way. When we talk about equal times square, energy, mass does not magically go poof. It turns into something. It turns into photons, generally high energy photons. Same can happen with this. When you're talking about basically, let's say two massive neutron stars, and you collapse them and you got a black hole, supermassive black hole. Here's the, you can calculate it. Neutron star A was, let's say, once 2 solar mass. Neutron star B, it was 2 solar mass. You should get a black hole which has a gravitational effect of 4. Again, it has gravity. There is no way things can get out. But turns out the resulting black hole was like barely 1.5. Like, what the hell happened to else? All that mass turned into energy and dissipated through space-time. That is the critical aspect. Space-time can leach energy away from you. So you can take two neutron stars and they are orbiting. Technically, they should orbit till infinity because there is nothing that can cause drag on something that massive. What the heck causes the drag which forces it to collapse? Because again, in our satellite is either solar wind or our atmospheric drag. These things cause a drag. What the hell is causing drag on neutron star? And not to mention they are orbiting in vacuum. So what the hell is there? Space-time. Drag on space-time will slow them down, and that's how we finally figured out like there is actual gravitational waves. But again, if we kind of mathematically say we observed a two neutron star, Einstein's equation was like, okay, we're gonna run the equation. According to equation, in this around 40 years period, we should see this much shrinkage. Basically, their orbit should shrink by this much, and we got it. Mathematics approved. So we know this happens. We know it allows us energy dissipation. So you can be like, hey, this collision happened, like two black holes collided, but their mass suddenly decreased, which should not make sense. There is nothing that can bounce off of a black hole, at least in a split second. Hawking radiation is a very slow process. So what the hell happened? All that mass turned into energy and got dissipated through space-time continuum. So this ripple, while technically is massless, it has energy dissipation. That's a very tricky aspect. So stellar collisions are generally very big source of gravitational waves. Now, scale is the critical aspect. When I specify everything is causing it, you have to understand everything is causing so minuscule it's worthless to talk about, because technically even moon causes gravitational lensing. But can you observe it? Good luck with that. Maybe in future with some weird technology, but right now the only thing where we can reliably observed is a solar eclipse, and sun is causing a 2.5 degree bend or something like that. So you can understand that it's a very big event. So same goes here. The scale we are talking about is very minute, very minute. So everything causes gravitational wave, but most things cause like 0 point Google, something like that. So basically useless. But big space-time fabric is very strong and stable. It's not even like you cause an event, it's gonna break apart. It's like it can handle it. It's like it has a very high recovery rate also. So massive events like black hole collisions, supernova, hypernova, kilonova, basically neutron star going into black hole, being intimate and all that jazz, they cause events. Now if they are far away, because if they are close enough, you don't have to worry about anything else. You will be destroyed just by the energy release. Like a supernova event has enough gas ejecting out of it, enough radiation ejecting out of it, that you don't have to worry about whether the gravitational wave is going to get you or not. These things will annihilate you. So when they are far away, what kind of effect we can observe? The effect we can observe is 10. So basically you take 0.1, not 0.1, basically 0 point minus 18. What does minus 18 mean? That means 0, put 18 0 there and then put 1. That's what it means. So it's like a ludicrous number. So to give a simpler context of that, you have to understand atoms are mostly empty space. 99.99% empty space. So you take that atom, you go to nucleus, like the very dense core part. Take that, go into it, and then little bit of movement. That's how much change is caused by two black holes getting intimate and making a one massive large black hole. So it's ludicrously tiny, and these are massive things that are causing something that little. So you don't have to worry about big things are destroying us. No, if there is anything that can be close enough where it's gonna damage us by gravitational wave, something else would have destroyed us beforehand. So we don't have to worry about it. So scale is very critical. Like it is very tiny. Now, what about detectors? Like how the heck we are detecting something this minute? Well, we take a laser interferometer. Basically, lasers, you have to understand, they are made out of photons. Photons are a weird because they have particle and wave-like properties. And wave-like properties allows us to do what we call cancellation. You can send one laser beam, split it out, send one way, this another way, and then you can bounce it back out of a mirror, properly aligned mirror. And once they come back, if you designed your system correctly, they will cancel each other out. Again, you have to fine tune it and all that. What will that mean? That simply means you can send let's say 1 watt laser or 1 megawatt in this scenario. You send it out, they come out, and once you detect in detector, it's 0. Why? Because those wavelengths are perfectly cancelling each other out. So you're not getting anything. It's like blink, blink, blink. Even though laser is continuously, you're getting blink, blink, blink. So these once the length changes, it starts to affect that pattern, that beam pattern. I have provided video down below, you can check that out. Now in real life they will show you that pattern either going black and white or something like that, but because of the sensitivity of these equipments, they are not aiming for going on off. What they are aiming for, brightness dip. How little the brightness dip, because again like it's like a proton thickness, like not even a full proton going off, like a surface of a proton going yellow. So the instrument is ludicrously sensitive. Now you would be like, okay, if the instrument is that sensitive, wouldn't it detect every other thing? Short answer, yes. That's why we had to build two of them. The reason for that, let's say you build two of them, you detected a signal, but let's say that was caused by an earthquake in Japan. Based on triangulation, you will figure out if that's what it is. So you don't have to worry about it. And because of the amount of data being generated, generally computers source through it. So whenever you see the images of like actual wave signal and it's looking like this, that's not the real signals. The real signal is noisy signal like this. Computer is shifting through it continuously. It's like reading through data, and it's like compensating for normal known patterns. Basically, if big train moves by, that's how much waves would be there. Earthquake, tectonic shift, moon moving around, and all that. So computer is just shifting through the garbage. And if it finds something unique, it's like, bro, this does not make sense, this does not match the database, then it's like, okay, forward it. It's basically the same how Large Hadron Collider does its work. So once you have detection in point A, same time if something else detects in the detector 2, then you're like, okay, now we have something else. And based on you will run the simulation. It's like, dude, is it caused by earth based things like earthquake or tsunami or something like that, or like big nuclear test or something like that? Once you filter all those things out, then you're like, okay, now it's coming from space. Then you will run trajectory data, basically where it's supposed to be. If its celestial sphere is outwards, so that is why making two is very critical. And nowadays, because we have becoming more confident, we have 3 or 4 working together, and based on that, now we can fine tune it. Like, this is the place, look at this celestial place, you're gonna find your object. So this is a very critical aspect that you have to understand. We have to have two. We could not reliably predict with one. We had to have two. So based on time system and all delay on that, you can fine tune on a celestial sphere, where the heck we are talking about. Now, what is the benefit of doing all this jazz? Well, reality of it, this is right now astronomy. I'm not talking about normal science day-to-day. In normal day-to-day science, we have a lot of instruments. But when it comes to astrophysics, we have nothing. Other than electromagnetic wave, we have nothing. Nothing. Like, do you know there is a star? Well, you can see its light. That's it. You have nothing else. Let's say there is a dust cloud. What is behind that dust cloud? Let's say that dust cloud is very opaque to every kind of electromagnetic spectrum. What is behind it? You don't know. We have only one tool, and that is electromagnetic spectrum. Now, thankfully, that spectrum is very wide. So you can take a photograph, let's say in Hubble case, and you will like, fingers of God, fingers of creation is very interesting. You take ultraviolet. Now it's a different thing. Now you can see different things. Same will go with X-ray. Now you are seeing something different. So it does allow us to see multiple different things, but all of them have simpler, similar kind of properties. So they are basically electromagnetic radiation. This is the only thing that is not in electromagnetic radiation. It's literally sounds of the cosmos. Let that sink in. It's tangibly vibration. What is the vibration? Basically sound. So we are hearing black holes going boom. So that is very interesting aspect of that. Now, when I'm specifying stellar objects, I do mean big things. Right now, we are limited by our sensitivity, like how sensitive our equipment are. But big things like a supernova, hypernova, kilonova, all these things have big. They also create sound. Now, what is the benefit of that? Like that, what's the point? I can see that. Like, you can have a telescope and it's like, hey, there is a supernova there. What's the benefit is that you cannot detect what the hell happened to the core. Mathematics will not support it, because all you're gonna get is a bright flashlight, because EM wave would be saturated. However, the gravitational wave is transparent. Basically, what does that mean? That simply means there is nothing in this universe that can stop a gravitational wave. So you can have like a giant gas cloud, and their signature is messed up in that gas cloud, but the gravitational will go through it without any issues. Like, who cares? And that's the interest. Basically, we are taking a microscope and we can see how these stellar event happens. Like, you can literally see, this was the massive of the star, this is how it was rotating, and this is how it collided, and this is the sound it made. Now, technically calling it sound is a bit of a stretch, but you get the point. So it's the only way we can see death of a star. That's why the fact it is transparent to everything. Basically, everything is transparent to it. A gravitational wave can go through anything. It can go through star, even black hole. I would not be surprised. So that's the benefit of, we can see, like, we got a different kind of senses. We only were limited to electromagnetic, but now we have something different that is priceless. So what we can expect in the future? Well, reality is, even though mathematically everything is creating a gravitational wave, we are not aiming to detect everything. We are not aiming to detect like a moon passing over us. We are not aiming for that. However, we are trying to aim where we can detect basically big stellar massive objects, basically supermassive black hole at the core of our galaxy and things of that nature. Basically, we do want more resolution, where rather than okay, one supermassive neutron star went boom, only able to detect that. We do want to improve our resolution. So That's the reality. Every engineer is working on improving that. How they are improving that? Basically making as many as we can make. So that's one way of improving it. Another way is basically put it in the space. Now benefit of that is because the more you stretch the basically arms of the interferometer, the better it will get. So idea is you're gonna put 3 satellites and you can put them in different orbit, and benefit of that, you can have 10,000 kilometer arm rather than limited to like basically in Earth case like 4 kilometer long arm. You can have 10,000, and that way you can become far more sensitive. And it's the same way, like same way we make a optical telescope bigger to become more sensitive, same can be done with this. And being in space, it allows you to be insulated from almost everything. So that's the next step, and more people are working on getting this done, like European Union, Japanese space agency. A lot of people are working on getting a like at least first prototype done, because there is some big ideas, like some big bonkers idea about making a like satellite based system that is like almost as big as a 8 light year, I'm saying 8 light minute in terms of diameter. So some big bonkers things can be done if you have a laser powerful enough, but people are working on it. And if we figure this out, if we truly start to make something big and bombastic like the space-based laser interferometer, we can detect many things and we can fine-tune it. And it has already happened where it's like a gravitational wave was detected, then they specified, okay, in this location point all your telescope there, and then we spotted a supernova. So that was the amazing aspect of this technology. It allows another kind of tool. Before that, it was like detect everything in this spectrum or that spectrum, and only then it will work. Right now we have something else to hear through it. So future is kind of amazing about this technology. So this was my presentation on gravitational wave. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.